afternoon, everybody. It's 12 o'clock, so we'll get started. There is a clock in this room, but I don't entirely trust it, so I'll pretty much just try and go by my cell phone time. So we'll start at 12 and finish at 12:50. So a couple of things to mention. Labs do start next week, so make sure you go to your lab period. You don't have to do any special preparation for next week, I don't think. The Lab Bright Space page is open. Dr. Lee has posted an announcement, so just check things out there. Assignment 1 is now open. That's based on the Waves chapter that we're about to get started. So we're good to go on the course. Last day, we did a quick review of simple harmonic motion. We've got a couple of bits to finish, and then we should be able to get started on chapter 15 today. Before we get going, does anybody have any questions? Okay, so we're good to start. Super. Typically before every class, I do have a slide like this. One is a review of what we did last day. The other is a question for you to try. The point of these questions is to just check in and see, did I get it from last class? You know, if you can look at these while we're sitting here getting ready to get started, if you more or less know how to answer these questions, then you're definitely on track. So that's the point of these, is to keep you on top of things. So I'll have one of these for every lecture, which is at the end of the course an extra 35 problems for you to work on. So they'll be up, pretty much every single time. And I'll always post the answers. Sometimes I'll put solutions, typically just answers. Depends on how hard of a question it is. So last day, we got through the equation for position as a function of time in simple harmonic motion. And the example we first looked at was a mass on a spring. We saw it oscillating up and down. And then we said we were going to think about the horizontal case going back and forth, and we wrote our equation for x. We took the derivative of position, and we got the equation for velocity as a function of time. Important to remember that velocity is a vector, so the sign of the velocity was important. A negative sign in your velocity means it's moving left, a positive sign means it's moving to the right. We thought about what the maximum velocity was, and we figured out that that was a omega. The next step now is to figure out what is the equation for the acceleration of something moving with simple harmonic motion. So we know that acceleration is the derivative of velocity. So we'll say follow the steps. I think you all can pretty much do this derivative. I'll post the steps for anybody who's not entirely sure. And anybody who needs a reminder, come see me and we'll just kind of work through it step by step if you're really rusty on your derivatives. When we take the derivative, we see that our acceleration as a function of time is equal to minus capital A, the amplitude, times omega squared, where omega is our angular frequency, 2 pi over t or 2 pi f, times cosine of omega t. What this equation tells us, and it's consistent with what we know, is our cosine goes as omega, just like v and x do. It means it has the same period in the acceleration. So acceleration has exactly the same period as position and velocity do. That's because it has the same angular velocity. Acceleration is a times omega squared, so the units will typically be meters per second squared, or centimeters per second squared. So those are our units of acceleration. Because acceleration has different units from velocity or position, we expect a different maximum in acceleration. It has different units, it has to be a different thing. If we want to figure out the maximum acceleration, we can do the same thing that we did last day with velocity. We know that cosine is a periodic function. It goes back and forth between +1 and -1. The biggest cosine could ever be is +1. So if cosine omega t, whatever omega and t are, if cosine of that is equal to 1, what we get for our acceleration is a is going to be minus a times omega squared times 1. I would argue that that negative sign means it's not a maximum. If cosine omega t were is -1, then our acceleration is minus a times omega squared times -1. Minus times a minus gives us positive. So our maximum acceleration would be a times omega squared. Okay, so there's our maximum acceleration. One sort of interesting thing about acceleration is you see that acceleration has a cosine in it and position has a cosine in it. These two things are probably related, so we can see that they should be related here. If I write my acceleration, a of t is equal to, I'm just going to swap the a and the omega squared, minus omega squared times a times cosine omega t. Then we recognize that this bit is actually our position function. So our acceleration as a function of time is minus omega squared times x as a function of time. Okay, so that's a useful bit of knowledge. What that tells us is if we know the position at any time and we know the angular frequency, we can go ahead and find the acceleration at any time. Okay, last, maybe I'll just call this a tip here. Last thing to keep in mind, if you're coming from physics 1020 or 1050, you probably remember those kinematics equations, x is v naught t plus a half at squared. Probably really used to using them and use them all the time to solve all the problems. Those equations applied to things with constant acceleration. You know, a was 9.81 meters per second squared. A was 3 meters per second squared. We see here that a goes as a cosine. A is not constant. Okay, so acceleration is not constant. So that means don't use kinematics. Kinematics only applies for constant acceleration. I mention it because once in a while you're in a test and you're working really fast, your instinct is probably to use kinematics, but that can set you astray when you're doing this simple harmonic motion kind of stuff. Okay, any questions here? All right, so this bit is fine. So the last little bit we need to cover about simple harmonic motion before we start our waves. And this last little bit is tricky. Some people maybe struggled with this a little bit in physics 1050. So please do ask questions if you have any as we go through it. So far, all of the graphs of position that we drew all started at the amplitude. Okay? Every graph I drew started at the amplitude. What that means, in an experimental sense, is that if I got my mass on a spring going, when I started taking my measurements, I hit my stopwatch when it was at the top of the oscillation, when it was at the amplitude. Okay, so that's what that means. That's when I started collecting my data. Now let's ask the question, what if I didn't start my stopwatch at the top? What if I started it somewhere in the middle? How would I write down those equations? Okay, it's a little bit different, but it's not really different. So if I drew a graph that didn't have the position starting at the amplitude, but started over here instead, it's fundamentally the same picture, it's the same oscillation, it's the same motion, but it doesn't start at the same place. So how do we account for the fact that it doesn't start at the amplitude? Okay, so now our starting position is right here. X of 0, so our position at time t equals 0 is less than the amplitude. The way we account for this is with what's called a phase constant. So that's a new thing. And what it means is that our graph is just shifted a little bit. So when we write our equation, our position as a function of time, it has the same amplitude, so we still have A. It's still a sinusoid, so we still use cosine. It has the same period, so it has the same frequency and the same angular frequency, so we still need omega t. What we have to add in is our phase constant, which has the Greek letter phi for the symbol. Okay, so this bit right here is the phase constant. symbol is the Greek letter phi. This would be in radians. So whenever you are given a phase constant or you have to find a phase constant, it would be in radians. So this phase constant essentially allows us to shift our graph to a different starting point. So let's double check that that actually works out. So if our t is equal to 0, then our position at time t equals 0 is a times cosine of omega times 0 plus phi. So our position at time t equals 0 is a times cosine phi. Cosine of phi is always going to be less than 1. So our starting position will be less than the amplitude. Okay, so this checks out. So in general, this is going to be our equation that you would use for position in simple harmonic motion. For velocity, it's minus a omega sine omega t plus phi. And acceleration is minus a omega squared cosine omega t plus phi. Okay, so same form of all of the stuff we just did, and that same analysis all counts. We just add in the phase constant to make sure we know we don't have to start at an amplitude. We could start anywhere. Questions? Good? The idea of the phase constant is okay? Okay, this phase constant idea is going to come back when we do our wave chapter, and we'll do more examples then, how to find it, what it means, and all those sorts of things. The next slide, if you've had a look at the notes I posted, that's a set of homework questions. It covers 2 topics. The first is a basic vector analysis. I'm coming to this course assuming you're comfortable with a vector analysis. If you're a bit rusty, I do have some things posted on Brightspace for review, especially the scalar product and cross product. You can, of course, come see me, and the Help Center is there as well. So if you need to brush up on your vectors a bit and you need a little bit of extra help, please come see either me or the Help Center. And then question 2 here is just a kind of a comprehensive review question about simple harmonic motion. You can use that to make sure you're good with all those concepts. I'm going to post all those solutions so you can check your answers as you go through it. Okay, any questions before we move on? Looks like we're good. So now we're going to start chapter 15. Chapter 15 is all about traveling waves. Oh, the picture looks terrible. I'm going to switch over to the computer because that picture looks better. Okay. If it would come up, it would look better. Okay. Here's the guy I'm envious of. I'd love to learn how to surf. I think that must be so fun. So we're going to start to study about waves and traveling waves. When we think about waves, probably a water wave might be the first thing we think about. It's such a common thing that most people have experienced. We're going to talk about waves in a physics sort of way. So we're going to think about waves. How high are they? How far apart are they? How fast are they moving? How much energy do they carry? So those are the things we're going to talk about when we study waves. We're going to do some things in general, and then we're going to focus in most of our times on waves that are started with a source moving with simple harmonic motion. So that's where we're going with this stuff. Here's one that we're going to have a little class discussion about in a few minutes. This is maybe my favorite kind of wave. Oh, sorry, I'm going to turn the volume down, then I'll hit play again. This was taken at the Rogers Center a few years back, not by me, but... So you see it here in the people? Okay, so that's the wave. So what we're gonna do is we're gonna talk for a little bit, and then I'm gonna come back and I'm gonna ask you if you think the wave is really a wave or is it not a wave. And I will give you a heads up that this is not a settled answer, so it's a little bit contested. So I'm gonna rely on you to think for yourself and decide what you think your answer is. Okay, so we're gonna come back to this. And so our chapter is about, and we're going to be discussing traveling waves. A traveling wave is defined as an organized disturbance which travels through a medium and has a well-defined speed. So that's what we call a wave, a traveling wave. This well-defined speed, this is called the wave speed. That has a symbol of a lowercase v, so v for speed. If we think about a water wave, somebody is going to throw a rock in the middle of a pond or a puddle, and you're going to see the ripples spread out. And the ripples spread out with the speed v. So our wave is those ripples spreading out, and it says here a wave is an organized disturbance. What do we mean by a disturbance? Well, the disturbance is those ripples in the wave. Then the last word that might be new is a medium. What do we mean by medium? So our wave here is the ripples spreading through water. The disturbance is the ripples, it spreads through water. Water is the medium. So the medium is the substance through or along which a wave moves. So there's our definition of a medium. When we think about that wave after you throw your rock in the water and those ripples spread out, it's interesting to ask, what is the water actually doing? Okay, so this little bit of water, and all the bit in this circle, it rises, then it falls, and it settles down. This bit of water rises and falls, that one rises and falls, all the way out as it spreads. So the water alternately goes up and down, but the water doesn't go anywhere. Like water doesn't go from here to here. It all stays put, it just goes up and down a little bit for a short time. So what actually moves in a wave? What do you think?
Particles?
Particles. The particles definitely move. They move up and down, and that's what makes the disturbance happen. So I agree that the particles move, but I think I'm going to disagree that the particles themselves go from here to here. Okay, so they do move, but they don't get transferred. You know what I mean? Okay, anybody else have a different answer? Yeah? Energy. Okay, who likes the answer of energy? Anybody been to the beach before and a wave comes in and hits you? Kind of feels like it's going to knock you over. Or maybe you've been to a concert and the sound coming out hurts your ears. That's all energy, right? So energy is absolutely the thing that's transferred, that moves from here to here by the particles of the medium vibrator. Okay, so the energy is the things that transfer. So that's pretty interesting. When we talk about our traveling waves, we have two kinds of traveling waves that we're going to study in this course. We have mechanical waves and electromagnetic waves. The electromagnetic waves are really neat. We're going to come around to those in the second half of the course. They're actually an oscillation of an electric field and a magnetic field. It can move through a vacuum, so an electromagnetic wave actually doesn't require a medium. Okay, that's kind of interesting. So the light that comes from the sun, X-rays that come off of an X-ray machine, those things don't require a medium. They can travel through anything. So they're coming up in the second half. Yeah?
Wouldn't the medium in that case be air if it's
Well, light comes from the sun to us. There's mostly vacuum between us and the sun.
That's not like a space.
Yeah, but there's nothing there. It's empty. Yeah, it's absolutely nothing there, right? That's interesting, right? It's really cool. How can light be an oscillation of a wave? That's a weird thing.
Like, there's nothing there.
There's nothing to oscillate. The thing that oscillates is the wave, right? We're going to come to electric fields, and hopefully we'll be able to wrap our brains around it a bit more. Yeah, but totally weird. Anybody who thinks it's weird is right. It is weird. Where we're going to settle in for a little while now is mechanical waves. So our definition of a mechanical wave is that we have a wave that propagates through and disturbs a material medium, like a water wave. So it goes through the water and it disturbs the water particles up and down a bit. We have to have a source. We have to have something to start a wave. Maybe we throw a rock in the water, or we turn the music on our phone. And the little bits have to push and pull on each other. So the water molecules have to push on each other to make that disturbance travel. Okay, let's go back to the wave. So in light of our definition of a mechanical wave, what do we now think about the wave? Who thinks it is a mechanical wave? Who thinks it's not a mechanical wave? How many people just don't want to commit? Okay, got some non-committers. Okay, so from anybody who was brave enough to say they think it is a mechanical wave, do you want to defend your position? Don't have to. I just invite you to if you choose. For anybody who says it's not a mechanical wave, would you care to defend your position? Yeah.
The energy is not passing.
The energy is not passing.
They are not touching each other, or they are not pushing each other. So.
Okay, no touching and pushing. Okay, anybody else want to add anything? Okay, for me, I fall down with that argument as well. So people are doing the wave. You could do it in class if you were really loose, but maybe not on a Friday. So people put their hands up, and the person next to them puts their hands up. I don't think everybody has to buy into this. If you started the wave over there, the people in the middle could just decide not to do it. They're not pushed. Okay, so for me, because there's no physical interaction, I say it's not a wave. Your textbook disagrees with me. Your textbook says it is a wave. At the Shoreland household, this can get a rather vigorous argument sometimes. We split 50-50 on who says it is a wave and who says it isn't. So I like this example in particular because a lot of physics isn't settled, right? There's a lot of ideas, there's a lot of discussion, and those kinds of ideas and discussions are very good things to have when it comes to physics. I think this, I see this, no, I see this, and I see that. Okay, so we'll try and keep that up as we go. Ultimately, we do talk about a lot of settled physics in this class, just because you got to go through it. So now let's focus in on our mechanical waves a little bit more. Of our mechanical waves, we have loosely three kinds. We have a transverse wave, a longitudinal wave, and we can combine both of those to get a combination wave. I brought a slinky that I can demo. Would anybody volunteer to hold one end of the slinky for me? Yeah? Thank you very much. Okay, all you have to do is hold it still. So I'm going to come across here. It should be long enough for us to spread the classroom. Maybe you come towards me a little bit. We'll try and center it. Okay, so the first wave I'm going to generate is a transverse wave. My hand is going to be the source. I'm going to start the wave, and I'm just going to flick it up. Okay, so you see the disturbance goes along. My coils do move up and down a little bit, but they don't ultimately go anywhere. And the wave we can see moves back and forth. So that's the feature of our transverse wave. The particles of the medium move up and down. The wave, the disturbance moves back and forth. Those two things are perpendicular. Our other wave is the longitudinal wave. This one goes fast. For the longitudinal wave, again, I'm the source. I'm going to squeeze a few of these coils and I'm going to let it go. Hopefully everybody can see it. I'll try it again. Okay, one more time, the disturbance is still going back and forth, you can see it, but it's going back and forth because my coils are moving back and forth. So this time those two motions are parallel, that's a longitudinal wave. Thank you very much for your help.
You're welcome.
And then a combination wave, we won't go through those, but combination waves are often found in water. You get some perpendicular motion and some parallel motion. If you think that's kind of neat, you might enjoy an oceanography class. So in both cases, we have a source. In our transverse wave, the elements of the medium, the elements of the slinky, move perpendicular. And in the longitudinal, they move parallel. In both cases, the disturbance moves with a wave speed v. So they both have that wave speed for the disturbance. And when we say that the coils move relative to the equilibrium position. Okay, so when the slinky is not moving at all, that's the equilibrium bit. So these parts here where it's completely relaxed, that's the equilibrium. Equilibrium could also be called the relaxed position. St. Mary's University has a really nice simulation here, so I've got that here if you want to look that up online. Okay, questions so far? Yeah?
Waves and fluids, are they ordinarily combination waves to some degree or another, or the transverse and longitudinal waves through fluids normally, or are they usually discrete phenomena?
Fluids are typically a combination wave. Yeah, fluids are really interesting. Yeah, and really complex too. Fluids is great. Physics does have an oceanography department, or physics and physical oceanography. Anybody who finds that interesting might like an ocean science class. Yeah, but we're going to focus in on transverse and longitudinal. We won't get to those combination ones. So we're going to look at transverse waves for a while. To look at transverse waves, you can try this simulation. This is really neat. I'm going to use these FET simulations a fair amount in this course. If you Google FET wave on a string, it's going to take you to a simulation where you can start all sorts of waves. I've got one propped and ready to go. Right here. So what I've got is a string. Okay, the string, it's got mostly red dots. It's got a few green dots. I'm very sorry for colorblind people. Clearly nobody who works at Colorado is colorblind. So if you can't see the red and the green difference, really all you have to know is that sometimes you're going to look at one specific dot. So I'm going to get it started. It's got a source here that starts the wave, and I've chosen to let my wave go right out the window so it doesn't have an end point. It's just going to keep going. So this is a wave. This is the kind of wave we're going to look at for a while. And some things we notice about this wave. In a second I'll turn this off and we'll make some notes on a slide. First of all, yeah, that's going to keep going, is our source here moves up and down with simple harmonic motion. I've set it that way. I've chosen it to go that way because a lot of the waves we look at will have a source that moves in simple harmonic motion, so we choose to study these waves. And in fact, light and sound are all this kind of wave. That's one of the reasons we study them a lot. When your source moves with simple harmonic motion, your wave is called a sinusoidal wave. So this wave that we're looking at here, that's a sinusoidal wave. So we're going to study those quite a bit. We notice that we have high points and low points. These high points are called crests, and the low points are called troughs. We have the disturbance moving along the wave. So the disturbance just moves, or the bump moves down along the line. I'm waiting for it to start again. So the disturbance moves along the line. That's got a wave speed v. And we see that the height of the string depends on position and time. Okay, so where it is, how far it is from equilibrium, it depends on where it is and what time it is. So these are all things we're going to be talking about. So I'll switch back to here. Some of the notes I've already got written down for you, but we'll label a few things on the picture. So this is our source. That's moving up and down with simple harmonic motion. I'll go SHM. So that means all of the equations we wrote down in our review, they all apply to how this source is moving. When we get a source moving with simple harmonic motion, it means our wave is called a sinusoidal wave. The high points are the crests. The low points are the troughs. And these middle points are the equilibrium. Right, so shorthand for equilibrium is just EQ with an M next to it. The height of the string has a symbol of Y. If you have one of the older textbooks, it might use a D for the height of that string. So it depends on which book you have. Our book, Young and Friedman, uses a Y. The height of the string relative to equilibrium, it depends on two things: where you are along the string, so the horizontal position, and also what time it is. Okay, so these are all things we're going to look at. And where we're going over the next few slides is how do we write down this equation for y of x and t. So that's where we're going with this next. Any questions so far? So the first thing we're going to ask is, how does any one piece of the string move as a function of time? So I'll just switch back to that simulation for a second. So we'll focus in just on one little bit. If you can see red and green, you can choose to look at one of the green dots. And we see that each one of those little bits, one of those little balls, moves up and down over time. So we're going to ask what happens at one single position and how does that move over time. So that'll be our first bit in our analysis that we do. So when we focus on one little tiny bit of the string, we see that it goes up, comes back down, goes back up. That's what it does over time. If we graph it over time, we see that it goes up and down like a sinusoid because the source is moving in simple harmonic motion. So each little bit of string is moving with simple harmonic motion. It goes up and down, back and forth between the positive amplitude and negative amplitude. And we know how to describe something that's moving up and down with simple harmonic motion. That's what we did in our review. So y of t, so this is for one element, one single piece. And when we make a plot of the position of one single element as a function of time, some books will call that a history graph, so you might come across that terminology. So one element as a function of time moves up and down between the positive and negative of the amplitude. So the maximum is A, that's the amplitude. It's moving with simple harmonic motion, so we have a cosine. The source moves up and down with simple harmonic motion. It has a well-defined frequency, so each element has the same frequency, omega. Omega is our angular frequency, 2 pi times the frequency, or 2 pi over t. It changes with respect to time, and let's not insist that it starts at the amplitude. Let's throw in our phase constant. Okay, so any one bit of the string moves up and down with simple harmonic motion, so we know how to write down that equation. So that's the descriptor of how the string moves as a function of time. Questions? Okay, so this gives us our time variation. We said it depends on time and space. So that one's just a review. Let's also look at the spatial variation. To look at the spatial variation, we have to ask, what does the wave look like at any one specific time? If we want to know what it looks like at any one specific time, all we have to do is hit pause. Okay, so now this is one bit of time. We can ask what happens with respect to position. When we do those graphs, we call them snapshot graphs because it's a snapshot at one spot in time. So for this one, we see that it is sinusoidal in space. It still goes as a sine graph, okay, a sine or a cosine. So it's sinusoidal in space. It's got a characteristic. When we had our wave as a function of time, it repeated over a certain amount of time. This is our wave over distance, so it repeats over a certain amount of distance. Okay, when we have a graph as a function of distance, it repeats with distance. So it has a characteristic distance. It goes from amplitude to amplitude over a certain distance. That distance we called the wavelength, and it has a symbol of the Greek letter lambda. So lambda is the wavelength. It is a distance, so it has units of meters, sometimes centimeters. And it's the distance for one cycle. A shorthand way to say that. Or the distance between any two crests. Another way to say it if you want. So this graph, the height still goes between plus and minus the amplitude. It still goes as a sinusoid. The only difference between this graph and the last graph is this one depends on x and the former one depended on time. So our equation for y as a function of x for one time it's going to have the same amplitude a times cosine. It depends on x, so we have to be careful about what we put in here. I'm going to get both these things at the same time. When it repeats over time, the thing that goes before the variable is 2 pi over the period. When it repeats over space, the thing that goes before the variable x is 2 pi over the wavelength. Okay, so there's our characteristic distance. And then we still have a phase constant, we put that in there. This gives us a new definition. 2 pi over the time is the angular frequency. 2 pi over the wavelength is called the wave number. So that's a new thing. You probably did not do that in Physics 1050. So we're going to define a new thing. K is the symbol for wave number. 2 pi divided by the wavelength. It has units of radians per meter. The radians comes from the 2 pi, or just meters to the -1. A little bit of caution here. Physicists use K for like everything, so don't get your K's mixed up. When you're looking at K on a formula sheet, make sure you know if it's the spring constant or kinetic energy or wave number or what it is. So just be careful with your variables there. So this graph is our spatial variation. Okay, good so far? So before we put those two things together to get the full description, we're just going to do a little tiny bit about the wave speed v. So the speed of the disturbance is the wave speed. That had a symbol of v. So let's find a way to write down our wave speed v. So there's our disturbance moving down the line and out the window with a speed v. You know that speed in general is given out as distance divided by time. If we wanted to look at one cycle specifically, then the distance for one cycle would be the wavelength. And the time for one cycle would be the period. Here you might remember that 1 over period is the frequency. That would be the same as f times lambda. And then if you threw a couple of 2 pi's in here, so omega is 2 pi f. F is omega over 2 pi. K is 2 pi over lambda, so lambda is 2 pi over k. If you put those things in, we get omega over k. So this gives us an expression for our wave speed. V equals f times lambda equals omega over k. I would argue that this is probably the second most important equation in physics. Anybody who does 1020 or 1050 with me, I always say 20 years later, the only thing you should remember about physics is F equals ma. That one should be stuck like forever. I would add this as the second equation to remember about physics. V equals F lambda. This one's really important. This equation, I do expect you to remember it. I probably would not put this one on a formula sheet because I expect you to know this one. Okay? So I think this one should not be onerous to remember. Okay, so there's the equation for the speed of a traveling wave. V equals F times lambda. Let's do a quick example, and then we'll get back to our y equations. The speed of sound in air is 344 meters per second. What's the wavelength of a sound wave if it has a frequency of 784 hertz? For musicians, I kind of corresponded that to a note on a piano. I sadly am not musical and I don't know much about the notes. So the first part of that question, let's find the wavelength. So part A, we know V is 344 meters per second. We know that F is 784 hertz. V equals F times lambda, means lambda is V divided by F. 344 meters per second divided by 784 hertz. The wavelength of that wave is 0.439 meters. So V equals F lambda. If you know 2 things, you can find the third. Then it also asks, how many milliseconds does each vibration take? So that question is, what is the period in units of milliseconds? So our period T is 1 over the frequency F, 1 over 784 hertz, equals 1.28 times 10 to the minus 3 seconds. There's our period in seconds. Then you might recognize that 10 to the minus 3 seconds is actually milliseconds, so 1.28 milliseconds. Okay, so we found our wavelength and our period. Then last, what is the wavelength of a sound wave that has double the frequency or is 1 octave higher? So for part B, we want to find lambda. That's V over F. We're doubling the frequency, so we're going to end up halving the wavelength. 344 meters per second divided by double the frequency equals 0.219 meters. Okay, that one's super straightforward. With this little bit of information now, you can definitely get started on your assignment. There's a few questions about wavelength and frequency and stuff. Okay, questions to here? All right, let's start setting up and see how far we get with the next bit. So our goal for the next bit now is we know that if we look at a history graph, that means what happens in time for one bit of space. We know that that's our equation for the height. We know if we take a snapshot, so that's what happens over space for one bit of time. This is our equation. And our question, what we're going to try and figure out, is what happens when we put the 2 things together. So what do we get when we combine those 2 things? If we want to get our expectation down, if we look at these two equations, we know that the height of the wave goes between plus and minus a, so our answer should depend on the amplitude. They both go as a cosine, so that should as well. One depends on x, one depends on t, so we expect both those things. We should expect omega and k, t and lambda, and we should expect our phase constant. So this is what we're expecting to find in our answer. This is the form we're looking for with all those things, because we know those are all important. So we want to make sure we really know what it is we're looking for. We want an expression for the height of the string as a function of every position and every time. So let's start by looking at our wave on a string. Let's take one snapshot and let's look at the wave when t equals 0. So that's what our string looks like for all positions when t equals 0. It does have a disturbance. It's moving forward with the wave speed v that we've already talked about. The equation for this wave, we know what this equation is. We've already written this one down. We're just going to change our equation a tiny bit. When we wrote down the equation, we said y of x and we closed the parentheses. This time I'm just going to put a comma and put a 0 in. So this is our string height as a function of position at the specific time of t equals 0. That's all that 0 there means. That's equal to the amplitude times cosine 2 pi over lambda, that's our wave number k, times x plus 5. Right, so we've already done this bit. We wrote this part down. So this is the descriptor of our wave at t equals 0. Our wave is moving to the right. So let's ask, what happens to our wave? Where is it? What does it look like a little bit of time later? Well, the thing that happened to it is it moved to the right a little bit. So I'm going to trace out my wave at t equals 0. So I'm just copying that one down from above. Here's t equals 0. It moved to the right a little bit. I am keeping an eye on the time. We've kind of got 3 more minutes left. So a little bit of time later, it's a little bit to the right. So this is some small positive time later. Time t. Good so far? So it moved to the right a little bit. So how far to the right is it? So it moved a little bit. We know it moves with speed v. We know it was moving for time t. How far it is v times t. Okay, so distance is speed times time. So the amount of distance it moved from here to here is delta x equals v times t. Good so far? So now what we want to do is we'd like to pick one point on our graph, let's say right here at position x, at time t. So this position is x, this time is t. We want the equation y of x at this time t is equal to. Here's the tricky concept. Here's where people tend to get a little bit lost. So we'll try and make it nice and clear. The height of the string right here is the same as the height of the string right here. We're good? So it's the same as y of x and 0, but at this distance delta x behind. So it's at this point instead. This position is, i.e., it is at x minus vt. Okay, that's the hard part of this entire proof. Any questions? We good? So this equation, y of x and t, is the same as this equation, but instead of at x, it's at x minus vt. So that equation is a times cosine 2 pi over lambda times x minus vt plus 5. Okay, that takes us to 1249. I am going to quit here. What we're going to start with on Monday is just making this equation look a little bit nicer, multiplying our 2 pi over lambda through. If you want to get a head start on that for Monday, you certainly can, but otherwise we'll finish it when we're back then.